So I'm going to speak about trees for logic and parsing. So let's first tell who I am. Yeah. So okay, I have been always interested in the implementation of logic, and I have tried to do this in C++, but it's very unpleasant in C++. Because because of many problems. C++ is not just designed for this. You have the memory management problem, and you have the problem of the polymorphism. And I have always done it in C++, and I got frustrated, and I started looking at other languages. Right, there's special languages designed for this, like Haskell or OCaml. And then but they also have their problems when the program gets bigger. You don't have containers in all these languages. So I came back to C++, got frustrated again, and this is kind of an ongoing cycle. And okay, so roughly then, let's continue. Let's first continue with the next slide. But it doesn't want to react to this. Why does it not react? Okay. So first about myself, I've always worked in teaching and research. That means that I was never, a productive member of society. Then I currently just work in Nazarbayev University. Now, before I have worked at University of Wrocław in Poland and at Max Planck Institute in Saarbrücken for informatics. And I have always been interested in logic and theory improving. And I have been looking at other languages like Java, Prolog, also Haskell, also OCaml. But somehow I always return to C++ because C++ has very many advantages. But yeah, it's just not suitable for logic. Okay, then let's go down. Somehow it doesn't want to react. Oh yeah. Some words about my employer, that's also important. So it was established, Nazarbayev University was established in 2010 with the purpose of building up a European or American-style, Western-style university in Kazakhstan. And to really to give first-class education and first-class research in Kazakhstan. So currently we have 4,000 undergraduate students in different schools. And so we have all the STEM fields, but there is also sociology, how is it called, management, and what else? Yes, so that's it. In order to work or to study at Nazarbayev University, you need to speak English. Otherwise, you just have no chance. So that's important. All important decisions are merit only. And for example, the admission exam is graded abroad to make sure that there will be really no politics involved. And so I work at the School of Engineering and Digital Sciences. There are 2,000 undergraduate students, I think, and 300 graduate students. Okay, well, let's move on. Okay, I already told part of this. So I got frustrated about C++, but also about the other programming languages. Then, roughly in 2020, I started a project to develop a programming language specialized for logic. This was, and out of this came. I started with the parser, which seemed to be the easiest part. And this was my CppNow 2022 presentation. So it's my second time here. But this time I really speak about the core, about the logic. So I think Maphone works nice. Try it out. I'm going to make some improvements in it, but I have been using it like 1.5 years now. I like it. There's no. Okay. So while working on the compiler for this language, the idea was to translate into C. So I studied the question of how to efficiently represent logic in C, and I made some progress on that. This basically happened, say, in the spring last year until the summer. And then last year during the summer, I thought, why not use, kind of embed these C data structures in a C++ implementation. And then maybe that will be usable. And it turns out very usable. So it is very nice, technically efficient, and I think based on what I have now, C++ is really my first choice for implementing logic. For me, it's a game changer. The students are using it to implement Zermel or Frankel's set theory, and it goes very smooth. And so I created a generator which takes the definition of an inductive type, and which produces a C++ code, and it takes like 1 second to do that. So I consider the problem of implementing logic in C++ completely solved. So what made this possible? Let's say that I didn't have 5 years ago. So there are two things. One is I became better. I found a new implementation method, and the concepts are essential. But Yeah, and then about the final project, I have to deliver a programming language. I'm just not sure about this anymore because it became, from my point of view, so much easier to implement logic in C++ that maybe I should. I'm just not sure. I will think in the summer and make a decision if it's useful to continue this project. Yeah, something about programming languages, right? There are here people who want to develop a new programming language to take over the world and be the successor of C++. One should be much less ambitious. You should design a programming language that solves your own problem, and if your language is the best solution for some for application area, that's sufficient, and you already have a right to exist. One should be a bit more modest, I think. I mean, if you look at Bjarne, he also didn't want to take over the world. He just had this problem of this simulation of an operating system, and he tried to solve that and nothing else. So, and then if you're lucky, you win the lottery. But if not, then okay. Okay. So it's all about trees in computer science. And especially logic is about trees. So if you have a formula like this, so not A and B, this is actually equivalent with A and not B. So and this is the tree representation. So you must be aware that whenever I write a formula, it's really about it's a tree. So the equivalent is on top, and then you have here the negation, and then the implication A, B. These are variables, and here's an AND, A, not B. It's a tree. So. Okay, since I speak about parsing, so this is just the slide is just state from the previous presentation 1 year ago. So in parsing, you also have trees, and you also. In parsing, it's somewhat easier to represent the trees because you have less operations on them. But if I would implement, if I will implement parser now, I will use the same representation because it's so much easier to use than dealing with smart pointers and with what are these things? Called polymorphism. I kept the parse tree here because it would be now also my first choice for implementing parse trees. But it was not really my original goal. But the title says trees for logic and parsing, and I keeping the promise. Okay. Okay. So what is really important for me? I really the first point. What really matters is a nice interface. So you want. Right, you want some recursive definitions. They're pleasant to read. Then you start coding them, and it becomes it becomes dragging. It becomes unpleasant, and you somehow. So if you want to get anywhere, the logic, the data structure for logic must have a nice interface. Okay, and then the second is the implementation, of course. But actually, this is not right. This is important here. Actually, this shouldn't be here because it's not the most important thing. The thing that matters is the interface, and that really means the time implementing the data structure. That's important, right? If you have a representation, there are two people. There's the person who designs the representation and the person who uses it, and it's typically the same person at different moments in time, and both want to not to spend too much time. So if before I would spend maybe let's say a weekend implementing, a logic, and then after 1 week I understood that it was not completely right. You want to modify it, and maybe another weekend. So that's what I here speak about. But this I can do now in a minute with the generator. So this is totally gone. Then this interface problem is solved, and this just should be gone. And efficiency matters, but not that much. I mean, it shouldn't be too bad, but. Efficiency is a goal as long as it agrees with the interface. But as soon as you have to somehow give up on the interface for efficiency, then you probably shouldn't do it. And the efficiency is mostly efficiency of rewriting. I will give examples, and you will see what it is about. So as a general rule, you must avoid reallocations. I will see what this is about. So I will give just a few examples of. I'm not really sure how is your background. Or of the video watches. So I give examples of logics that one could typically care about. So lambda calculus. So lambda calculus has a simple recursive definition. So you have this is really the simplest form of lambda calculus. You have variables which are lambda terms. You have, if f and t are already lambda terms, then f applied on t is a lambda term. So there's only univariate application. And if v is a variable and t is a lambda term, then you can lambda vt is also a lambda term. Right? This are the three cases. And this is about the simplest form of lambda calculus. If you want, you can add types to this, and then you would have a separate recursive definition for the types. And some systems mix the types and the terms, and then it gets more complicated, but this is really the simplest definition. So okay, here already you see an option. So if you are given a lambda term, and you don't know anything about it, your first question is, which of the three cases do you have here? So, and I will call these three options the states of the term. It's a bit an imperative term, but so you are given a lambda term, and you want to say to do something with it, whatever it is, you will need to find out the state first. So there are three states. And I show a few operations on the lambda terms that typically occur. So one thing that you could do with it is check if a variable is free in a lambda term. So it's a simple recursive algorithm. So if you are given a lambda term, if the variable is free in it, if it's in the first state, so it's a variable, and this variable equals the term, the variable that you're looking for. That's clear. Yeah, and then if you have an application term, the variable is free in it if it's either in the left or in the right free. So you have to check both cases. Yeah, and it's free in the lambda term if it's not this lambda, because then it will be bound. If it's not this variable, because then it will be bound. And it must occur in the body. That's the definition. So that's easy to say. Okay, then I'm not really sure how much I should go into this, but I think I have enough time. So there is something like substitution. So you have a lambda term, and you want to replace a variable in it by something else. So that's called substitution. We all know how to do that. So this is in principle easy. So if you have a variable and you want to replace a variable by some other term, you should just check if the variable that you have at hand, that is the variable that you want to replace. So if it is, you get your new value. Is it written here? Yes, you get a new value. If it's not, then substitution does nothing. Okay, so substituting in an application means substituting in the left, substituting in the right. This is so in terms of okay, so that's what it means. And substituting in a lambda term is a little bit tricky. You may know this, because it could happen that this variable occurs in this term, and then the meaning changes in an unwanted way. This is called a capture. And so what you have to, in that case, you have to find another variable here and put it, also replace it in the term, and then do the substitution. And this is so if this variable doesn't occur in you have no problem. You can just recurse into the term. And if it does occur, you have to do two substitutions. One for finding a fresh variable, and then do the real substitution that you wanted to do. So if I would implement this in real, I wouldn't do it like this. I would use the Bruin indices. So if you know, you can, instead of variables, you can somehow put kind of pointers, counters that count back to the lambda that you're meaning. Because this problem is annoying, and it can be solved. But you know, if you say if you want to implement it as a toy, you could use this definition. I actually I used it so. But if really somehow efficiency is your goal, you shouldn't do it like this. Okay. Then there's something called beta. So you know beta reduction. Yeah, beta reduction is if you have a lambda. So this is a function applied on a term. You can substitute So you can substitute the variable in the term. I mean, this is what lambda calculus is. This is the same what lambdas in C++ are. So you have a lambda, you apply it on something, then only the compiler, C++ compiler, will not substitute, but it will remember the variable, the value of the variable, and then evaluate this term. But logically, it's substitution. Right, so if you have a reduction in the left, then the complete term reduces into this one. But if you can try to apply, basically this definition means that you must apply reductions everywhere, as much as you can. And if you're lucky, you obtain a normal form, and that's the outcome of your computation. So this is what I described on the previous 3 slides is a complete programming language. But this is how logicians. Okay, something more. I like to tell this. So lambdas sound exotic, but they're really not exotic. So they're everywhere. Everywhere where a function is constructed in mathematics, there really is a lambda. So if you look at this like this, I mean, mathematicians will tell you that this is a very small step or something, but it's really a lambda. So you have a function, and the integral takes a function and gives you another function. And in order to define a function, you need a lambda. So this is really lambda t and then e to the minus t times ft. And here, you see, mathematicians don't know how to. They should just remove this t. They don't understand that that the function is a closed object. So you write either lambda t ft, or you just write f here. But that's still, this is, by the way, definition of Laplace transform. I understood, I still suffered from learning this, but I understand it's not taught anymore because people now use numerical methods. This Gaussian formula, let me say, this is sigma is really a function that takes a function and a beginning point and a start point, right? So it's really sigma applied to lambda I square, and then from 0 to n, that's that. So lambdas are everywhere, just that mathematicians don't know about them. That's their problem. Okay. Okay. Yeah, here is. I have to think a bit about the time because So this is another example, term rewriting. So we have another recursive definition. So we say 0, false, and true are terms. It's by the way untyped. So if t is a term, then the successor of t is also a term, and successor of t means t plus 1. It's like a number. So not t is also a term, but this is somewhat assumed that the thing is a Boolean, but the language is untyped. And I don't know, factorial I also put there, but I'm not using it. Then you have plus t1 times t1 and equal t1. These are also terms. And then you have another case, which I just put it there because it could occur. So if you have terms and an identifier, then ft1 up to tn is also a term. This leaves somehow place for functions that exist, but that you don't want to evaluate. So, you don't know their arity, so this is why you have a general unbounded number of arguments. So this term, this is a second definition, has 4 states. So 1, 2, 3, 4. You can see them. And what you typically may want to do with them is something called term rewriting. So again, you want to evaluate terms. So you just whenever you see plus x0, it's x, right? X plus 0 is x. But whenever you see x plus y plus 1, it's actually x plus y plus 1. So, and you have a couple of more of these rules which actually don't really matter for the presentation, but you must just know that there are such rules. And you want to apply them. So the idea is you just want to apply them wherever you can as much as possible until you reach a point where you cannot apply them anymore. And then you have calculated the outcome of your term. Right, so yes?
So when you say rewrite rule, you're talking more like just you recognize that part of the tree, you totally drop that part and replace it with the other.
Yes, yeah, so you just go through the tree, you check, for example, for an occurrence of plus x, it's kind of a structural matching. And if you see it, you replace it by this. And you keep on doing this until you don't find any of these patterns anymore. And then you say, this is the outcome of my computation. Okay, but I said you do not, but these are the typical things that I want to implement. So we had this lambda calculus, we had this one, and there's another example which for example, you may want to do like this: 3 times 2 plus 1 equals 1 times 2 plus 3. So you may want to check that. So then this would be your expression. So this successor 3 just means successor of successor of successor, but it doesn't become readable. But that's what it really means. And then you rewrite this, and eventually you will get through. Okay, but this is important. Yeah, and this propositional logic, I mention it because it has a special difficulty. But it's a third case. So a propositional variable is a formula. If f is a formula, not f is a formula. You have binary operators, implication and equivalent. And you have operators of which you don't know the arity. That's important. I just wanted an example that has this unbounded arity. So I mean, you can say or and are just binary operators, but that's somehow not a natural way to think about it. So suppose you would want to implement, you have a way of implementing them without any compromise, then you would certainly go for the unrestricted operators and not make them artificially binary, right? And I don't want compromises with the implementation, so that's why I put this example. Okay, so here there are 4 states, and in the last state the number of subformulas is unbounded. And this gives some difficulties which need special attention. Okay, now what comes next? Okay, so the question is, we want, let's say we have our favorite logic or something else more complicated and we want to implement it. How are we going? What are the typical things that we want to do? You have to have a clear picture. What are the operations that really you do with them? So one obvious thing is you construct a tree, right? You have this definition. It tells you how to obtain new trees, so you can. You can just construct let's say you have two formulas, you want to construct the end of them, you need a constructor for that, or at least a factory or whatever. Okay, then if you for example, if you apply performing a substitution, you need to determine the state of the tree, and then once you have the state, you can access the subtrees as const. Yeah, and the problem here is already the problem start, because not always all subtrees exist, right? If you have a lambda term and you want to access, say, its function, its left term, this only exists when it's in the second state. So that's the problem. So you have subparts which only exist exist dependent on the state. Right? So this is somewhat. And then you may have accessing and replacing, and this is important for rewriting. So if you want to do rewriting, you want to replace subtrees. Okay, now you could say, I'm not going to replace subtrees, I just take out the subtrees and then construct a new one. Right? One could take this, then you don't need to do this. But then you're always reallocating. You pay a performance penalty for that. And moreover, it is kind of unnatural. I mean, so it is. You want to have this operation replacing subtrees. Okay. Yeah, and then in the case your number of subtrees is variables. So like here we had here with then you may want to change the number of subtrees. That's reasonable. You may want to remove the last, or you should at least have popback and pushback. So that's here. So that's here. So that's case 5. This is important operation. This is why I put it here. This is why I put this propositional logic here. Well, lambda calculus doesn't have this, but propositional logic would have this. Okay. Yeah, and in the case of you have this variable, right? When you have a variable number of subtrees, then this here, decomposing and constructing a new one is not a real option if you want to construct a new tree. Right? Do you understand this? Right? So that's because you want to replace one subtree, you somehow have to take out all the others, and you don't know how many there are, so you would have to put them in a container, and then reconstruct somewhere in this container, put your new, make the replacement, and then put it back. That would be really, that would really spoil the interface. So this must be separate operation, and it especially matters when the number of subtrees is unknown. Okay, so that's it. So time flies. How much? Maybe it goes okay. Yeah. Now, but wait. We started 5 minutes late. Wait. It doesn't fly that fast. Okay. Okay. So my goals now are to have a nice interface for the programmer who uses them, to have, of course, automatic memory. And that means automatic memory management. But this is not a challenge. We know already 20 years, 30 years how to do this in C++. But to have value semantics, that's really important. We don't want side effects. Since trees are implemented with pointers, and as soon as you have pointers, you run the risk of having reference semantics. It shouldn't happen. We want value semantics. And we want statically type checking as much as possible. And this is problematic because of the states. The states escape the static type checking cannot deal with the states. But we still want it as much as possible. And then we want efficient, which means for the moment means to just minimize the number of reallocations, and try to be local as much as possible. So we're going to need pointers, and we want to minimize the number of pointers, the number of indirections. And also probably to put as much as possible before the pointer. Okay, now, okay. Okay, now come the implementation choices. So what choices do we have? Right, I said this already, we're going to need pointers. So the question is, what is before the pointer and what is after the pointer? What do you put local and what do you put on the heap? And so alternatively, where do we put the pointer? Do we put it before the data or after the data? Okay. Then this is important choice: sharing, not sharing. Yeah, so as soon as you have pointers, it becomes tempting to share. We should not share. And then what else? And then and representing the state polymorphism. Okay. Right. Of course, implementation is not completely disconnected from interface, but we should still try to think about them as different, entities. Yes.
When you say state polymorphism, are you talking about the different types of nodes?
Yeah, about what I like, just the cases of the definition. So you have these subtrees, you have these trees. They have four cases in that definition. These are the states.
Okay.
Okay, so how do we determine the state? Well, I used a couple of options. So now we're going to get a bit technical. Well, I speak about it as interface, but of course it's also implementation. So you can use an enumeration type and then use a switch, right? There's nice switches. I like switches. They are nice. They give readable code. And so you just put a switch on, say, on the top operator, and then you know in which state the tree is, and then you can continue with it. You can use a chain of ifs. That is, that doesn't lead to, I think it's not readable code in the end. I mean, you can do it, and it's also not so efficient, but it's still an option. Then you can use a visitor, right? So you could, like variant variant is also different states. You can just have a visitor, which is a function, which then takes additional functions for each state that this variant is in, and then applies and then it gets out the subterms or the data and applies it on the function. Right? So this you could use visitor, and you can use inheritance. This should also need to be wrote. Or you can just right, if you have a function, you can somehow scatter it through different subtypes, and then let's just call the function on the base class, and it will find the sub case. Right, so these are the four options. So 3 is theoretically nice if you would use. Now, if you would teach Lambda in certain systems of Lambda calculus, it's the only way. But it's too rigid. So it's nice for simple operations, but the problem is that you always have to provide exactly one function per state. This is okay, say, where we have this is-free variable, then it's easy. But like if you want to have rewriting and you want to recognize a case, then you don't want to do this with a visitor. Because right, you have only certain patterns you want to do something with, and with the other patterns you want to do nothing. But the visitor will still force you to find something for these patterns that you don't want to do anything with. It will become very unpleasant, the interface. So I think 3, although theoretically nice, is ruled out. Okay, right, and so sometimes you want, if you have a single state. Right, let's have the propositional logic. You have the state binary, but you still have different operators for them. So sometimes you may want to distinguish them, and sometimes you want to treat them together. And then, right, if you have a visitor, you kind of lose this flexibility. So yes, and you may also want to handle 2 trees at the same time. For example, if you want to check if they are equal, do a deep check. Then visitor is not going to help you. Then you need something. A kind of visitor that takes both of them at the same time and decomposes both of them at the same time. You can write it, but it gets unpleasant. So, yes. So what about 4? Yeah, so 4 is using inheritance, right? 4 is using inheritance, but so the main problem with inheritance is just that it's not the right tool for this. This is not how logicians think about algorithms. Right, so if you use inheritance, then a function with the same name is scattered through all of the types, and this is okay if this function is kind of characteristic for this type. But logicians will not think about this free algorithm. There is one function which has 3 cases, and you want to see them together at one point, and not when you. So in the case of Lambda calculus, you would define 3 types, one for each state, and then have a base. They have a parent class that is the Lambda term, and then you would write, if you would call is free, that it would be dispatched to the subtype, and then there would be the case handled. But it's just not natural. You don't want to see it like this. You want to see the code really at one place. Yeah, and Yeah, and it would have the same problem with the rewritings. I mean, you have this 10 rewrite rules. How are you going to dispatch them through the different subtypes? It's not going. It will not become a nice. I mean, if you really want, you can, but it will be terrible. It's not how you should do this. So, okay. So in the end, if you go through it, I think it should be one. You should use you should have an. You should have a tag in the term that is the main operator and be able to do switches on those. Then, and then if you don't like it, you can still implement other options, but one should be really available. Okay, then we are going to move on. I think now I'm really at 30 minutes, right? I think so. Maybe now 28, maybe 32. Okay. Okay. So I decide to take an enumeration type. Now then there are a couple of little, say, technical problems. So suppose you have different, suppose you have different tree types in your logic. This happens because you may have types lambda calculus. Then you have types and lambda terms. So do you make different enumeration types for them or use one enumeration type? So after having tried like several times, different enumeration types are annoying. Use one single enumeration type. And basically in the end use one enumeration type per project namespace. So yes.
Can you say more about what's annoying about that?
What is that?
Why is it annoying to have different enumeration types for the different nodes?
Because the names overlap. They usually overlap. And another problem with really because the names overlap. There's really no need. Yes. I mean, what would be the reason to put them different? So one reason that I in the beginning hoped is that the compiler will help you if you forget a case, for example, in the switch. But the compiler is of no help at all, is my experience. So that's really just put them together in a single enumeration type. And I usually call it selector because it selects the state. I mean, you cannot call it operator because operator is a reserved word. And moreover, it is not always an operator. Yes, and enumeration class is also not very helpful, I found. Just use simple enumeration. And the problem is that typically your enumeration tags have the names of logical operators like and or, and they are reserved words. So you cannot call them and or, so you have to prefix them by something. And as soon as you have to prefix them by something, you have no advantage of enum class. So just use simple enumeration. I mean, that is okay. Yeah, and the compiler is not helpful ultimately because logic is hard to type check. I mean, because of the states. And so then now, okay, we gradually go. Now there will be code in the end also. How much do I?
Excuse me, sorry.
Yeah.
So just now, I was thinking twice about what you just said, that it's hard to type check. But that's because if you just had your enumeration types, your enumeration values having a mapping to the type, you could represent your nodes with a type tag, and you could do checking at compile time on that.
No, I think not. So let me think.
Okay.
Now I will come to type checking. What is the problem with it? Okay. Okay, now I speak about problems with unbounded number of nodes of subtrees, like which you had in propositional logic. And I also added it to the rewrite system just to have it. But there exist trees that naturally have an unbounded number of subtrees. So you need constructors for this state. So they must be constructed from initializer list and from other containers. And if you want to construct from other containers, you do this through iterators, and this you really couldn't do without concepts. Otherwise, you would have different constructors, and they would get confused. But the concepts can somehow make the constructors overloadable. It's hard to give an example, but Right, you may have unbounded, you may have states in which you construct some different types of subtrees, unbounded. And if you would define constructors for those, then without concepts, these constructors would conflict and they would not overload. But because you now have concepts, you can add the subtypes to the iterators, and then they will not have overloaded conflicts. This is possible only since 2020, so it really has consequences for the interface concepts. No? Okay, but there is an annoying problem if you want to construct, say, a first-order a propositional formula with unbounded number of subtrees. You somehow have to put them in a vector somewhere else because you don't know how many there are, and then you need a constructor that takes them from this vector, say by moving if you want. Okay, so and this is of course not nice. And the same if you want to replace something, you would have to put them in a vector, make the replacement, put it back. So, and this is not nice. This doesn't work. This is annoying. What instead you can do is you can give the formula the tree factor-like behavior. Right. This is what I did. So instead of constructing the factor, you construct the formula and you push back in the formula. So this means that the formula, the tree, when it is in the right state, must behave like a factor because it has this unbound number of subtrees, right? So it must have pushback and popback, and you must also be able to assign to retrieve subtrees. So and then you don't need an initial container anymore because the formula becomes the tree becomes the container. Okay. Yeah, and this means also that for implementation, if the term is in that state, it must have a size and a capacity, and it must internally behave like a vector. So you need to do some low-level things in order to get that this interface. Right. So what is we? Yeah, I have to think. Okay, now we're gonna look at implementation. So I somehow showed the interface, most of the interface. There's some. So now we have some choice. So where do we put the pointers? Right. If we implement lambda calculus, let's suppose you could do it like this. I mean, I'm completely ignoring the existence of variants of any sophisticated data structure. I just look only at the low-level representation now in C. So you have a selector. Then you have a union which represents the state, and then you have a variable, right? You have a variable if you're in the first state. You have two subterms if you're in the second state, and you have a variable again in the body if you're in the last state. Right? And here is a choice, right? You have the star here, right? There must be a pointer somewhere because it's a recursive data structure. So, but if you follow the path from the term to the term back again, you have choices where you put a pointer typically. Right, you could put the pointer, but you could put this star also here, and then here can be this term just as a value. And here, this variable, you could decide to put it on the heap if you want. I mean, I wouldn't recommend it, but you can. And here the same, you can put the star here, then they are not needed here. Right, so you can do that. And then this struct will be on the heap and not local. So if you would do this, if you would want to put more on the heap, you would, for example, get this. Right. So now you have to define them in advance because yes.
So the term on your previous slide had a union of three different.
Yeah, it was the first example, the lambda term.
Mm-hmm. Yeah. Have you considered using stud variant for that?
Yes. Okay. Yes, I will tell you what's the problem. I will have a slide to it. Okay, so at this point, I'm not discussing the higher level interpretation because I'm just looking at, how to say, the naked representation. The stud variant still has a union inside. Mm-hmm. So, but the problem is, the problem with stud variant is that I mean, it's not a big problem, but you have different operators having the same state. And the variant cannot represent this. It internally has a tag which we cannot get access to, mm-hmm. and this tag has one value per state, mm-hmm. and we want different values per state. Like if you have a propositional logic and or, the formula is still in the same state, mm-hmm. and variant doesn't support that. Also variant, I think you cannot do a switch on the state. I think you should be able to do a switch. It's for the efficiency and it's just elegant. And variant doesn't support switches. Because it should be somehow possible to give names to the states with variant.
Mm-hmm.
I mean, I think variant is a great thing, but it has some weaknesses for logic. Okay.
I think there's some libraries that implement variant with a switch, so it's a little more efficient.
Good. Yes. Yeah, it's not really an efficiency question, but just an interface question.
Right.
Yes.
Thank you.
Yes. Okay, so this is the case that I mentioned it on the previous slide, that you can decide to put this struct below the pointer, and then you have to give a forward declaration first and then define it here. And the same with abstraction. Now this whole these two parts are on the heap, and this part also. And actually the string. And now this variable is on the heap, and this one is still local, right? But you could. I mean, that's a choice. I mean, this selector you could even put it on the heap, but I wouldn't do it because then questioning the state will become hard. Not hard, but slower. So. Okay, now this is a fundamental question. I also have to think, do I start worrying about the speed? I'm halfway now, right? Yes. I will think. Yeah, let me think about the time shortly. Okay, it doesn't make sense to speed up. I will see. So one important problem is that you need to decide, do you want to share or not to share? That's important. So right, as soon as you have things on the heap, then sharing becomes a temptation because if you assign, you can just copy the pointer and not copy the data. Right? So and this of course destroys, if you're not careful, you destroy the value semantics. But because if you know the problems from Java, if you have two values sharing representation and you modify one of them, then the other one will also magically change. And it's not the kind of magic that you want. So yes, if you look at C++, C++ has assignment on heavy objects like maps or vectors. So the C++ spirit seems to be to do not sharing. So that's maybe the first idea. But look at what the code becomes like if you have no sharing. So suppose you want to apply this rewrite rule. So times x successor y, it becomes plus times xy x. And you want to do the sharing aware, right? So you recognize the case. We decided that we use a selector for that, and so we recognize the case. Okay, now we don't want to copy because it's costly. So we move out I assume that is an iterator. So if you don't want to share and you want to walk through a term, then you're going to need iterators. So you would have 3 iterators. I assume that P is a 3 iterator, so. Then you would move out the parts that at this point we have recognized it, so you take out the parts, you move them out. Now since this x here occurs twice, you have to consciously make a copy of it. Yes?
In your if statement, you have you're calling the cell function twice, and then comparing it to 2 different values.
It's a selector. It's the tag that determines the type.
Mm-hmm.
But actually I look at the top is times, and then I look at, this is really wrong. Yeah, you're right.
Okay.
This must be, you want to know if this one is a successor.
Okay, thank you. I was confused.
Yes, that's right. I will make a note of that. Yes, okay. Thanks for the question. Okay. And then you construct a new one, and you have to everywhere put the moves in order to avoid the unnecessary copies. So in the end, you have not a nice interface. This is clear. You have to be all the time copy aware and think when to move, not to move. And I think it spoils everything. I think that is. So I think that this is not a way to go. So we go for sharing. Okay. But I will do it in such a way that you don't see it through the interface, because value semantics is kind of sacred for me. We're not going to give up value semantics. So, okay, I'll have to check where we are. Okay, Okay, I'm just looking. I'm going to show you some real code now. So how do we access? So once you have determined the state, you have to access the subtrees. And here comes an unpleasant feature. Once you have determined the state of the formula, you know which subformulas it has. But the C++ compiler and the type system doesn't know. So you have to do some kind of cast. And that's unfortunate. So you need to cast into a subtype or do something with it to convince the compiler that it is in the state and that the subterms exist, and then you can access them. And this is how free looks in my interface. So this is the implementation of isFree that I just gave in the beginning. I'm going to So you switch on the selector, then you have the 3 cases. So yeah, and here you have this view. You have to view it like a variable, and then when you do this, you can access the variable, right? And when you have an apply, you have to actually view it as an apply, right? And then you can access the subtrees and check if they're free, right? And this is kind of a proxy object that you could view it like a cast, but it is not a cast, but you can really view it like a cast. Well, it's not a cast because it doesn't change the object, but it opens a view on this term, and that views it as in this state. And yeah, there is no way around it, right? You would if you would use variant, you would also use it. You would have, how is this called? What is the function? Holds value. Is it called holds value?
Yes.
You have the same with variant. You would have the same.
Holds alternative. I think
Well, yeah, holds alternative. Yes. And there is no real, if you would use an invariant, a variant, you would still have to, there's really no way around this. And this is because, I view it as a weakness of the type system. Because we know that this exists, so it should be possible to do it without. But we have to live with it. But anyway, I think it's a reasonable implementation of isFree, so this is what it looks like, how it works. Okay, no. Yeah, this is what I already said. I will say something about refinement types. Okay. Okay. And let's check now. I want to say that we're going to run into trouble. So, okay, I skip this slide. Yes, no, I will do it. It makes no point to skip this. So I'm now going to, rewriting is an important application. I'm going to speak about how to replace subtrees, and that's a bit technical. So suppose you may want to, just simple example, you may replace the value v by another variable in a lambda. What you can just do is you can take out the subterms and construct a new one, right? But it's an allocation. So suppose if you don't want, and this is especially problematic if you have an unbounded number of subterms, because if you would want to do this many times, you're just moving the subtrees around and doing nothing with them. And this will make simple updates. So you go through the subterms and you update them one by one. If you have them take out all the others, this process becomes quadratic. And then your complexity is, your efficiency is gone. So if you want to, we want to update in place subterms, right? One thing that you cannot do is give out the reference, because if you give out the reference, the term may be shared. Then somebody could assign to it and then change the other term, right? So this we cannot do. We cannot give out the reference, but we can still do updating, Python-style updating. Right? If you know Python has no references, but you can still assign to subterms. But in C++, if you assign to a say to an element of a vector, then the vector gives you the reference, and then the reference with the value go to the assignment operator, and this operator does the assignment. So in Python, it cannot work like this because Python has no references. What it does, you have a ternary operator that takes the array or the vector, the index, and the value. And then does the update. Yeah, and this we can do also. So we can define for every field. So sub2 is a field of what actually? I think of this propositional logic, and we can define the update operator. So which takes the original formula and the view on the original formula and the value and does the update. Yeah, and the advantage of this is that this is safe. This updating can avoid the side effects. So you implement it as follows. So if the tree is right? If the tree is sharing, then you, and this you can see this from a reference counter. Then you make, and if it's distinct from, and the U is distinct from the current value of the field F, then you do a reallocation and assign to F in the copy. Yes. So, right. So this is this avoids the side effect, and you can do this because you have the tree. You still have the original tree. But this is important. So now how to check 2? Okay. Now how to check that you're not changing the value? That's important. So we are checking that we are changing the value. But this is potentially very expensive because we are dealing with trees. Right? And if we would do a deep comparison here, then I could stop now because it would be too inefficient. But what we can do is, so we have pointers, so we just compare the values up to the first pointer. That's it. So, okay, let's say if this would be Python or Java, I would say we check identity. So we just compare the references. But since we may have some values before the pointer, we should also compare those. So we compare the values up to the first pointer. That's in generally a cheaper operation because you don't put anything big before the pointer. I mean, maybe only a few integers or tags. So and I call this very equal. So very equal, it means just 2 terms are very equal if the trees, if they are equal up to the first pointer. So now the correct version is this. So one stays the same if the tree is sharing. Actually, this is wrong. The parentheses are wrong. So if the tree is not sharing, you immediately go here. I say this really wrong. So if the tree is it right or not? Yeah, the if is a bit. It's not really because the update you always do, of course, also when the tree is not sharing. When the tree is, but okay. But anyway, you do that. You do that very equal test, and then if it's the same, then you make the local copy and assign it a local copy. Right. So the purpose of this is to do this rewriting, where you say, this was example 2, where you do all these rewritings, and you don't want to reallocate. So yes. And there's some details. You should never assign to a selector, of course, because then you change the state and then you mess up the invariant. Yeah?
Are you able to compare the trees with some sort of hash? I don't know how many values up to the first pointer are being compared.
No, let's go back here. Where is the... Right, if it would be in this state, it would just mean I compare only the pointers.
Okay.
Yes, and if it would be in this state, I would end up comparing the strings. But there is no hashing. Okay. I mean, as a general, the local part is generally small, and in this case, it's nothing essentially. Only this, you would compare the selectors and the pointer. Okay. Okay, accessing subtrees. Yeah, okay. Okay. Yes. So. Yeah, I'm not sure I want to go immediately to the difficulties. I think I should show you some code still. That's nice. We like code. I think it's better to not save here with somewhere else. Say the Lambda. Okay. Where is it? Also, I'm looking at the wrong. Whoa! So I will turn off the sound. So I hope that can be cut out. Nee, where is it? Is that readable?
Make it a little bigger.
Bigger? Okay.
That's good. Thank you.
Okay. So here you see a case. Here you see these operations in action. So you're looking for possible rewrites. So these are the binary cases. So you have plus times equals. They have two subterms. Then you have to do this unfortunate view, and then you can get the subterm. You recursively try to replace it. So this is a top-down replacement. It makes from the top scene the first replacement, and then the result of this replacement you use for the update operator. And this is this update operator that I just showed. So if a replacement was made, then this term will be not the same. And then it will, if necessary, do a reallocation here. And the same here. Yeah. So we get out the second subterm. We recursively go to this same function, which is really called. Which really has this name, is here. Yeah, okay. Yeah, so the nice thing of this notion of very equal, you can use it to check if a replacement was made. So this is the function that actually makes the replacement, or it doesn't, or it returns the same term. Yeah, and if it returns the same term, it's very equal because it will not do anything with the data. So if this happens, then you know that the replacement was made, then you return. And if no replacement was made, you're going to try to do it in subterms. That's what this function here. Okay. So, yes. Yeah, so this is the update operator, which, if necessary, reallocates if the term changed, if the tree changed. Okay. So now you may ask the question. So I showed you in code. Where did it go? See, I don't see the document. Okay. I showed in the code. So do we, this is the question, do we now have the optimal reallocation strategy? Why does it not want to open? So no, the answer is no. This is in fact very disappointing. And I will show you what the problem is. Now, the problem is this: even if the term is not shared, this top-down function will always reallocate because when it passes the argument recursively to the top-down function, it's shared at that moment, right? Right. So if you're going to rewrite in a subterm, you pass this subterm recursively to the rewriting function, and as soon as you do that, this is shared, right? So this is the problem. So, right. Do you get this? This is kind of an important point. So, this is computer. No, Quest or what? No, it's not Quest. Not yet. So, right here you have this. Right, so this is a subterm, so you pass it to this term, and as soon as you do this, since it's a copy, the reference counter will be increased, it will be shared. So whenever it will be always viewed as shared, even if in principle it's not shared. So what solutions do you have here? Now, and this is a bit technical, so what solutions do you have? One thing is you could use move. Right, so you could try to move the function, but actually you cannot because we don't have because then you would give out we don't have non-const access, so we cannot move. Yeah, and we can also not make the argument of top-down const of the function. We could make it a const reference instead of a value, but then we cannot update because you cannot update the const reference. So that's not going to work. So we need to come up with a smarter strategy. Actually, I have to think about what I want to tell. Okay. And the solution is to borrow the subtrees during rewriting. So for this, I define something called extract. By the way, this is something not really that you would normally use. You would use this only if you really care about efficiency. I mean, for many applications, you probably don't care. But if you really want efficient rewriting, you need to deal with this. Okay. So we have something called extract, where f is a field again. So what it does is, if the tree is sharing, then it returns the field as a copy. I mean, it does the same as the previous, so that will then be sharing. And if the tree that you're extracting from is not sharing, then you return the field as a move. Yeah. So what does this mean? That means that this operation does not introduce a sharing. So, right, it could have been shared before, then it will be shared. But if it was not sharing, then the moving will not make it sharing. Right? So because the move means that the term that the tree that you're moving from gives up its ownership. Okay? Yeah. I'm not really sure what I want to tell you. I want to think shortly about the time. So, well, I still have 30 minutes, right? Maybe minus 2.
20, 23.
Yeah. Okay. Yeah, I would like to demonstrate it, but the main point is that if that's somewhere on a okay. Let me just demonstrate that it works. Okay. Maybe that's better than. Okay, I have an implementation that actually shows this if it wants to work. Why does it tell this? I did something stupid, it seems. So I may not have an implementation. CD programs. I did something dumb, but I'm so. Yeah, I'm not really sure if I should show this actually. But let me show you. You have two terms here, and you have the times, and this would normalize into something. Right? So this doesn't. So you take 2 times the successor of it. Right? So and then I do the rewriting with it, and I just want to show that it will be that it will not reallocate. But I'm not really sure how important this is now. Let us check it. What is this? We totally don't want to see. And it's showing us things that we completely do not want to see. So you could try to read this. Yeah. And the main thing is that this is a term, the successor of something. This is the state of the reference counter. And this is the address, kind of. And you see that the address didn't change, but it did make the replacement. So here's this times. And this times is gone in the copy because it's evaluated. So it replaced nothing. So now if I at any point introduce a sharing, so let's do that. Let's do this where? And let's just say, so one thing that you could do is just remove the move here. Okay, now from the point of the normalization function, this product will be shared because it's copied into the function, and it doesn't know that you don't care about it anymore. So. Right, and now we did the reallocate. Do we see why do we not see the reference counter here? That's curious. But it did the reallocation. But the question is, why did we not see the reference counter here? I would like to know. Because this copy is made in the function only. This is why you don't see the reference counter here. But I could, for example, do like this: auto copy is prod, and I could keep the move here.
So we're doing all of this so that we can rewrite a particular node and replace the.
Yeah, without reallocating, with minimal allocations. But I'm going to move, this is a bit technical. You see now, you see the reference counter being 1 here, being 2, and you see that was reallocated. So that's the main point. But I'm going to move on because in the end it's a bit technical and it's not the most important thing that I want to tell.
So what's the use case for having such high performance? I know your examples are here to explain like
that is rewriting. If you want to do the rewriting, so if you want to in the beginning use lambda calculus for calculation, then you're going to make many beta reductions.
Okay. Gotcha.
Yes.
So the trees could be huge.
Yes. Yeah, and the problem is if you make you have a sharing tree, then you make one replacement. After this replacement, it's not sharing. Mm-hmm. So it will always happen if you make many replacements. So you cannot somehow ignore that. Mm-hmm. It's not a thing that happens occasionally. It happens all the time. Okay, now. Yeah, did I answer your question about variant? Is it okay if I skip that?
Yeah.
Because I would have said it. It's the thing. And this okay. Yeah, so I'm suppose you could have a variant which somewhat where you can mention the names. I don't know if it's possible, but you have the state and the names of the text.
I think it could be something like that.
One could imagine that it exists. Yeah. Okay. Okay, now I want to say something. Okay, I want to limit. I want to skip the implementation details there on the slide, but internally how I implemented this, because what I want to do is. Okay, but I want to say something. I want to say something about the needed data structure. So, right, you have these cases that dynamically grow in size. Yes, and so they need a state. They need a size and a capacity, right? Because and you have to share it down here. And you have to store it down here because, like with a vector, the capacity must be different from the size because otherwise you would have to reallocate all the time, and a sequence of pushback will become quadratic. We don't want that. So and now, but this requires something that C++ doesn't have, right? So we have two things of a fixed type, and then we have an unbounded number of something else. And to the best of my knowledge, C++ doesn't support that. Right? You can use new, and then you can allocate an array. So then you get an unbounded number of elements of the same type. So this you can allocate. But you cannot allocate an array with something before it of another type. I mean, to the best, and that's what you need here. Mm-hmm. Yes. So it would look like this in memory. So you have this as the size, the capacity, and then this array. Yes, and so of course what you could do is you could put another pointer here. So here, this is you could introduce another struct where the size and the capacity are here, and then a pointer somewhere else, and then this is usual data, which you can allocate with the usual new array new. So. Yeah, and then here I give an example of another logic. It's not only the reference counter, the reference size that you want to put in on the reference counter, but it could be also some other data element. Right? If you have an operator, it could be a string with substrings, you may want to put this operator here. So we have I all the time have a case where you want to allocate something and then followed by an array in the same memory fragment, because you want to have as few indirections as possible. Mm-hmm. Okay. Yeah, okay, I will be on time. I see the problem. Okay, I have two data types for this. One is the scalar S, which is just this is almost like a smart pointer, a shared smart pointer. So this is used if you have no repeated fields, and this is with the repeated fields. So you have a repeated part and this scalar part, and this then comes in front of here. Okay. But I mean that there are some technicalities of how this is implemented, which I think is more or less obvious. If you, I want to say something. Right, this is all about merging the vector and the smart pointer about this data, but it's not. And I skip it. Okay. Okay, I want to. Okay. Okay, so if you would want what I just described implement by hand, it's very unpleasant. But I created a generator, which is very easy to use. So this is the specification of the lambda calculus in the generator. So I define this is the type that I'm defining. And okay, here are the selectors. So we have a selector var, then you have a variable, which is a field var, which is a string. And this, how it's called, hashtag means that it is local. If you wouldn't put it, the string would be on the heap. If you want the string to be local, you put a hashtag in front of it. So this is the apply case. It's recognized by cell apply. And then you have the function is a term and the argument is a term. Yeah.
It would be really, really cool to have a nice DSL, a nice C++ DSL for defining the types, and then also the rewrite rules.
What is DSL?
A domain-specific language. So using like overloader, operator overloading and things to make a DSL that may look something like that.
Yeah, but I have, this is real, I have a tool that generates the C++.
Yeah.
And then the lambda, again, the body is a term and the variable is locally on the, yes. You have the local field always, put a local field last, is why it is last. It's a bit counterintuitive, but it doesn't matter. It matters because the user doesn't see the order. Okay. Right, so this is how the definition in Haskell would look like. Yeah, so you can compare, in Haskell it would look like this. So in Haskell, these are the constructors. You don't give names, so this is why it's just lambda lambda, because you don't give names to them. Yeah, and this is, by the way, the definition of free in Haskell. So it is all matching based. Well, we can do some comparison. I mean, if you compare it to what I wrote, is it worse or not? I like the C++ more. It's a little bit longer, but the difference is not that big, I think. And also, if the advantages, if the examples get bigger, then matching becomes somehow harder. Yes. Okay, I have another example. I mean, this is this rewriting logic that I mentioned on slide 14, which has the. I forgot to tell something important, but I can tell it here. So, right, you give this is an option. I mean, I call them state in this talk. So you give the state, and you give the name of the state of the option, and then the selectors that correspond to it, and then after this arrow, the fields that belong to it. So unary is a successor, not or factorial, and it has one subterm. A binary is plus times equals. It has two subterms, which are called sub1, sub2. Yeah. Okay, this list-like notation really means list. So this is it means an unbounded number of subterms of type term. Yeah, and this means also that when the term that is in this state, it will have a pushback and a popback, and so you can push a term to it, and it will have indexing operators. Yeah, and the string is local. Okay, what is this? This is the selector. This is the state that the term has to be in when it is moved out. So I showed you that moving is important for efficiency, and you need to tell to the system, to the generator, what is the moved out state, and that's cell 0. That's 0, because in 0 it has nothing. So it's important that the moved out state holds nothing on the heap. So cells, but you could have equally put a cell false here, and just to define the moved out state. Okay, now how much time we have? Now I'm going to wrap up. So okay, I'm going to say something philosophical about which I would like to have. So I think there exist three ways of typing. One is static typing, which C++ has mostly, and Java and Oh wait, I call them. I list them in the wrong order. So the lowest level of typing are typed instructions. So this means that instructions have types built into them, and just assume that they work on a given type. And if they don't work on this given type, I mean, if you try to apply them somewhere else, it's just bad luck. Right? That's assembly language. Also, the C-style printf was like this. Right? So you write this %d, and then you apply it on an integer, and the print function assumes that it is an integer without checking this. I mean, I know that many compilers now check it, and also C++ I think has a checked version, but originally it was unchecked. So that's the lowest level of checking. Then you have dynamic type checking, duck typing. So that means that the data carries type information, and at runtime this information is used for selecting the right operations. Right? So this is, and then we have the static typing that the compiler checks at compile time, and then when this check is done, nothing needs to be done anymore. I mean, the compiler generates the right typed instruction, and so at runtime you don't need to know anything about the types, right? And C++ is mostly this, except when you use virtual functions, then you have a bit of this, right? So now, so what is here being used? right? So we have this switch, we have this apply, right? And this is this cast is problematic, right? This is a typed instruction, so it assumes that it is of the right type, and to generate this, and if this would be not of the right subtype, then something bad would happen. And then the rest is typed again. This is statically type checking. So once we have done this view, the view has the types, has the subtypes. And now if you think about it, it's really a weakness of the static type checking that we know that it is of the right type, and why can the compiler not know it? It happens in the same line. So it should somehow know that if the selector is cell apply, that T is in the state apply, and that this field exists. And then you could omit this line and just write here T instead of this P. Right? Okay. Yeah, and this is somehow the essential difference, I think, between matching and what I am doing. So if you would have matching, you wouldn't have this point. So matching, it determines the state, and then immediately extracts the subtrees. And because we don't do this immediately, but there is this point between it, we run into problems with the type checking. So. And I believe if one would have a bit better type checking, then one could get rid of matching. Because that's so.
You could do it with some template metaprogramming too.
Maybe, okay. Yeah, and then a similar problem is in the constructor. So if you construct, say, a lambda with a variable and a t, that's fine. But if you would construct, say, an application with a variable and a t, it's not okay. And so currently the type checker wouldn't know this. Inside the constructor, I have optional checks that check it, but it really should be statically checkable. Okay, so I'm going to end now. I don't want to overrun the time. So I believe that I solved the problem of implementing logic completely, at least on the interface side, because I have been using it maybe for half a year, and I have letting students implement logic, and I really like it. And the students are not complaining, so I think it puts C++ really back in this as my first choice for implementing logic. Then for the implementation, I should probably have a better look at efficiency still, because I should have a look in Compiler Explorer. Especially, I should have a look at what these views actually are doing if they have a penalty. I'm assuming that they have no penalty, that they get inlined away, but I'm not fully sure. I should have a look and make some measurement. Yeah, and then it would be nice to have an extended new that can allocate with a fixed prefix. It would look something like this. So you have a new, then you have the fixed type, then you have the repeated type, then you have a value for this s, because you need this needs to be initialized, and then you have a number that tells how many r's you want. Right? When currently you have this without s, you have only and without this s. This now exists, but it would be nice to have it. I don't know if there is a fundamental reason why it is not there, because it would be nice to have. And it's nice to dream about refinement types in C++. I don't know if it was possible even, because it's for sure if you want refinement types, you need absolute value semantics. Because if you don't have value semantics, then right, so you do this selection here, and then by the time that you're here, somebody else may have touched your data structure. If you would have reference semantics, this could have happened, and you cannot trust here anymore that this function exists. So if you want refinement types, you really need to be you need absolutely complete value semantics. But so we have this for our data type, but of course in general it doesn't exist. Okay. Then do I have? Now this is my. Let's see what I have. Do I have something more to tell? Okay. There is one important missing feature that I notice. You cannot generate template classes. So suppose you have this lambda calculus. You have your variables, and suppose you want different types of variables. You could say it is a string, or it is a string view, or maybe you want to use some normalized string. And then so you would like to generate your lambda terms as a template over the variable type. There's really no reason why it cannot be done, but the generator cannot do it. You could easily, not easily, but I could do it by hand, but I want that the generator can also generate template types. There were some other reasons, but it's currently missing. Okay, that is. I want to thank some people at my institute also, and that's all. So thank you. Is there a chair, or should I lead the questions? Yeah. Okay.
Does the generator, can it also generate the rewrite rules, or do you have to write the rewrite rules in C++?
Yeah. Well, it doesn't know what rewrite rules you want. So.
I mean, but can you define the rewrite rules in the generator and then have the generator generate it?
Currently not. This is not so easy. So. Well, you would have to implement it. No, it cannot be done in the rewrite. Where's the slide? So I will tell you, you have to make a choice. Do you want to hard code them in your program or not? Mm-hmm. So if you want to hard code them, you should just do it. I think that's maybe the best for efficiency, the best way. But if you would want to write, say, a general program that reads a set of rewrite rules, then you have to represent these rewrite rules also as terms, as trees, and then implement the matching by yourself.
I mean, the generator could generate the C++ code that implements the rewrite rule, right?
Yeah, it's possible. Yeah, it's certainly possible. You would have somehow, you want to optimize it, then you should look for common prefixes and somehow try to update. It's called discrimination tree. You could do that.
Discrimination.
So people doing C or improving, they will do this. They will, in the rewrite rule, merge all the common prefixes so that matching is efficient. That is absolutely possible. That's possible, yes.
So you said you have students using this, so is it available for us to play with?
Yeah, it's not finished. They are working on it, but it will become available. Yes. So they are implementing Zermelo-Frankel set theory, and they can now prove simple things like A implies A, and like for all A, but say a bit deeper theorems. They are working on the what's called Kuratowski pairs, and prove. You know what are Kuratowski pairs? Okay. So if you want to construct an ordered pair in set theory, you construct the set A, and then the ordered pair of A and B is the set of two elements containing A, and then the set of two elements A, B. That's called the Kuratowski pair, and you want to know that you want to prove that this is a real pair, so that you can extract the elements, original elements, and so they are working on this proof. And I think that's if they manage to prove that, then I think it could be released the system. Then we're going to have some fun with ordinals, where we will see. Yes. And so this logic has like 40 cases, and this is you really don't want to implement this by hand, right? You have all the subterm, you have unions, you have subset, you have what is it? What's called replacement axioms. There are like 40, and the logical operators. There are some proof constructors, and it has 40 cases, and then the generator is really useful. Mm-hmm. Yes.
So I was going to say, if you do use the variant, the pattern matching proposal does give you syntax that's very much like a switch statement.
What proposal?
The pattern matching proposal.
Yeah.
And then in lieu of that, you could roll your own stood overloaded, which would give you something very similar to pattern matching that you could pass to stood visit. Just in that case, you need to define your own fallback.
Yeah. Maybe can you do switches also on the state of variant?
Sorry?
Can you then do also switches on the state of the variant?
Yeah, that's what he's talking about.
Yeah, okay, I don't know. Read this, tell me later.
Yeah, I posted links on the Discord channel.
Okay. Yeah.
With the untyped lambda calculus, how does sharing deal with the Y combinator?
The Y combinator? You mean in combinatory logic?
No, I mean in the untyped lambda calculus.
Yeah.
The fixed combinator.
You mean the binary one?
No, I mean if the untyped lambda calculus has unbounded recursion. Yes. How does sharing deal with that?
I do not really understand the question. Unbounded recursion. You mean? You for sure don't have circular terms. They're always finite. Okay. Yeah. So I mean, logic trees are always finite, and even if they're unbounded, it's still finite. Does it answer the question?
Yeah. Okay.
Okay. You were also last year in my presentation, right?
Yes.
Okay, I remember. Okay. Anything else? No. So thanks you for listening, for asking good questions.